Hello everyone, welcome to Lab Today. Today it's about weather. Last week we looked at climate and how the average weather characteristics over time gives us an overall look at the climate. We're going to focus in on weather today. And of course, weather is invisible. We can't really see it other than maybe the clouds in the atmosphere. And so there are special devices we use to measure the different weather conditions like temperature, humidity, pressure, and a good way to visualize that and help us to predict weather in the future is to actually map those things out. And so creating a surface weather map helps us to understand better how our weather patterns are behaving and how we think they might behave in the future. And so today it's all about predicting weather and looking at the devices we use to measure it and how we actually go about constructing a surface weather map so we can better tell what the weather's going to be like later today, tomorrow, and throughout the week. So here we go. Let's talk about weather. All right, we begin our journey through this lab by looking at the background here, noting that weather stations throughout the world transmit weather data to the World Meteorological Centers located in Melbourne, Australia, Moscow, Russia, and Washington, D.C. And then that weather data is disseminated to the different weather centers for interpretation. It's of note that they use a universal system for time, the Greenwich Mean Time or Universal Coordinated Time. Meteorologists often refer to this as Zulu time or Z time. Thus, at any given location, weather is indicated in Z. 1200 Z would be noon, as an example. And the weather data is also given in a set of symbols, universal symbols. And the universal symbols are actually shown what they mean on the next page here, going through and describing sky cover and wind and what the fronts look like here, and then what different weather symbols used. But in general, these weather station models are shown in this notation. You can see here in the center is the location, and a little wind barb shows the wind speed and direction, so you know what the wind is like. You also know what the cloud cover is like. If the circle is completely colored in, that means it's overcast and cloudy. It even tells you the types of clouds right above here in the center and just below the weather station model there circled in blue. Additionally, you get temperature given, and temperature is usually given in the upper left here. Dew point temperature is given in the lower left, shown here in orange. The pressure of the area is given in the upper right, and that is right here. And the precipitation amounts in the lower right, which is given right here. Information about pressure is actually given below the pressure area here. And information about the precipitation, a little bit more information about the precipitation is given here. Additionally, they actually outline what type of weather is in the area, and that's given by the symbols that you see just to the left of the symbol. So this is all listed here, so you can kind of refer back to this and see what's what. But I kind of want to give you an overview of what the stations look like. And again, this page, the next page shows kind of an interpretation of the symbols, noting, for example, the different types of sky cover and what each of those symbols mean. The wind barbs are 1 to 2 miles an hour if they're alone. If they put a little barb on there, it is 5 miles an hour. A longer barb is 10 miles an hour, and any combination of those gives you different wind speeds. If it's going 50 miles an hour, they put a flag there, and so you can, of course, put those together to find the different kinds of wind. So the first part of this lab for me is to have you just kind of get familiar with these station models, because these tell us what the weather is at certain locations, and it helps us to analyze the weather. So the first question then is going to have you going through and looking at the different scenarios, 4 different scenarios of what weather station model is telling us. All right, and I'm going to go walk you through this most complicated one and have you do the other 3 on your own. Okay, so looking at this one, comparing our station model, we note that, of course, again, temperature is given in the upper left corner. So we can start there with temperature. And the temperature then is 27 degrees. So you can go ahead and write that one in there, 27 degrees. And so that's temperature here in the upper right corner, or sorry, upper left corner. In the upper right corner is the pressure. And barometric pressure is a funny one. For some reason, for reasons of not putting the entire pressure measurement in there, what they do is they give you usually 3 numbers. And what you do is you put a decimal point between the last 2 numbers, and you add a 9 or a 10 in this location here. You add a 9 if the number here is 50 or more, you add a 9. So in this case, we would add a 9. So the pressure here is 999.7 millibars. And the measurement isn't given in millibars. That's how meteorologists measure temperature. So you have to put a decimal behind and add a 9 if it's 50 or greater, or a 10 if it's less than 50. And so that's our pressure there. So our barometric pressure is 999.7 millibars. Okay. Just to kind of put a point on it, if we come over here and look at this one, we're going to put our decimal point between the last 2 numbers, and this is below 50, so we're going to put a 10 in front. So our pressure is 1011.7 millibars here. All right. Next is the dew point temperature, and the dew point temperature, the temperature at which the temperature needs to drop for dew to start forming, for the humidity to be 100%. So that gives us an idea of how much water vapor is in the air. The dew point temperature here is 25 degrees. The sky coverage here, right here, if we go back to our paper that shows us the sky cover, you can see that this would be overcast. So we would put overcast, or you could put 100%. We're going to go ahead and put overcast. The current weather right now shows 2 dots. Remember, the weather is shown off to the left here, and 2 dots indicate that it's rain. And if you go to the lower part here in the weather characteristics, 1 dot means rain, 2 dots means light rain, 3 dots means moderate rain, 4 dots means heavy rain. And of course, there's other symbols. As here, you're going to see the thunderstorm symbol in another one of these that you're working on today. But those 2 dots indicate that it's light rain. So we're going to go ahead and write light rain for the current weather. And the wind speed. Note that the wind barbs here are 3 long ones. So each one is 10. So 10, 20, 30 knots. And it's given in knots. Whoops. 30 there, 30 knots. And then we have the wind direction, and the wind direction is shown by the barb. The barb is actually pointing the direction the wind is flowing. So the wind direction is usually given from where the wind is coming from. And so if north is here and south is here, west is here and east is here, then the wind is coming from about the northwest. If you put north, northwest, you'd also be correct. So we put from the wind direction from where it's coming from. Where coming from. There's also extra information about pressure, as I said over here on this location, and the pressure tendency, when you have a backslash, it means it's falling, and when given a forward slash, it means rising. And so in this case, the pressure is falling, and the pressure change during the last 3 hours would be this term here, and it's given in tenths. So it doesn't put a point there, but it actually gives it in tenths. So you would actually put a point in front of that. So 0.11 for the pressure change, and you would say falling. Okay, and then we also have the pressure tendency. Oh, the pressure tendency we put falling down here, sorry. So, and that it's a backslash. A forward slash would mean rising. So use this information that we just went through to complete the other three for this part. The next section of our lab is dealing with isolines, and isolines are used to show visually what's going on a broader scale with the weather station readouts. Either temperature, dew point, pressure, wind. Isolines can be used to give us a visual of what's going on. And if, for example, you're using isolines for temperature, they're called isotherms. If you're using isolines for pressure, they're called isobars. Dew point are called isodrosotherms. And so we're going to work with these today, starting with temperature. And you can kind of see how these isolines here for this particular, these are isodrosotherms as in our example. What they do is they separate temperatures or dew points or pressures of equal amounts. And so it creates zones. And the lines are usually smooth and they're usually estimates. And so we're going to go through and kind of talk about these for temperature. So let's start with temperature here, or isotherms. And you're asked to create a 70-degree Fahrenheit isotherm and a 75-degree isotherm. Now, an 80-degree isotherm is already in here. And what you do to create an isotherm is you just draw a line between similar temperatures. If we're drawing an 80-degree isotherm, we're going to put an X where we think 80 is, and it's, of course, right here. And so then we would draw in our 80-degree isotherm here and draw on the line connecting points of equal temperature. The 75-degree isoline, or excuse me, the 70-degree isoline, will start there, would be where everywhere you see 70 degrees, and remember temperature is in the upper left of the weather station symbol. So we're going to put X's where we see 70 degrees, and it's in the center of the circle. That's where we're just going to connect those with a line now. And bada bing, bada boom, you have just drawn in a 70-degree isotherm. Okay. Lastly, we're asked to draw in a 75-degree isotherm. And of course, everywhere there's 75, you're going to put an X. So we're putting X's here and here for these 75. But you look and see this is 78 degrees. So what do you do when a temperature is not given of the same amount? This is 78 degrees and 70 degrees is here. 75 is going to be somewhere in between these two. And so I'm going to go to the place where 75 would be. If this is 70 and I'm counting up 71, 72, 73, 74, 75, 76, 77, 78, 75 would show up right about here between these two. I can estimate that 75 would be here. This temperature is 78, not 75. 75 would be here. 74, 73, 72, 71, and 70, okay? And again, then I'm going to draw in my lines connecting points of equal temperature to one another, just connecting the X's. And so I draw my line from here to here and then further interpret it that way. And there's my 75-degree isotherm. So you can see how isotherms or any isolines are drawn by connecting points of equal value. All right, and what this does is it shows us zones. You can say then between these zones it's 75 and 80 degrees. Between these zones it's between 70 and 75. And then you'll see on weather maps, of course, that these zones are colored in. And so you see, oh, I'm in the red zone, I must be 90 degrees or more. Or I'm in the orange zone, I must be 80 to 70 degrees there, etc. And so that's what these are useful for. We're going to go on and draw some isolines on a actual weather map. Now the description up here goes through and talks about what I just talked about, how to put an X in between to estimate where temperatures are. And I'm asking you in this particular activity to draw in 45 degree, 55 degree, and 65 degree isotherms. So let's do that. I'll put the 45 degree in red because it's cold, and 55 degree, I'm sorry, I'll put it in blue. For 45 degrees, the orange for 55 degrees, and the 65 degree red for warmer. Okay, so we started with the 45 degree isotherm. What I'm going to do is look at this map and see where it's 45 degrees. And of course, here's a 45 degree right here. can see by the temperature in the upper left there. So here's one place where I'm going to have my line go through. Here's another place that says 46 and another place that says 39. So I'm going to kind of start in this corner and move around. You'll see that because this is 46 and this is 39, 45 is probably going to be somewhere close to the 46 mark and away from the 39 mark. I'm going to put 45. I would put an X right about here, okay, to indicate that that's where it is in between the two. And similarly, between 46 and 38, 45 is probably very close to the 46. So if I'm going to connect those two lines, I just go ahead and do that. If I want to continue my line this way, where do I go? Well, 46 is here and 39 is here. Again, 45 between these two is going to be right about here. So I'm going to connect those two lines with that X. And then I want to continue to draw my line through. So I just go to weather station readings here. Between these two, 39 and 52, 45 is going to kind of be directly between them-ish. So I'm going to go ahead and put an X right here. And of course, here's a 45 right here, so the X would be right in the center, so I can go ahead and kind of continue my line through. Between these two, 42, 40, 45, let's see here, continuing on, 61 is here. Okay, and 42 is here. Between 42 and 61, where's 45? Probably right about here. So I'm going to go ahead, my line's curving in a different way. Between 42 and 61 then, 61 and 44 here. Where's 45? Probably close to the 44, so I'm going to continue my line here. Between 66 and 46 here, maybe right about here. Let's see here, 66, 46, so 45 is going to be right about here. In fact, 45 is actually right here, so I'll put another little line here. And I guess I can probably just go ahead and take my line this way. So it takes an interesting turn. You just have to kind of curve your lines as estimates. So my 45 degree goes off the map over here. Where does it go on this side? I'm going to come over here. This is 45. We got a 52 and a 39. So 45 is probably directly right between there. So I'm going to curve my line down to that point. Between 39 and 57, 45 is probably somewhere right here. So I'm going to continue my line this way. I can continue to use this 39 point. Here's a 54 over here. 45 is probably going to be right about in between, maybe a little closer to the 39. So I'm going to come over here with that. Noting that 43 and 46 are here, so 45 is probably going to be right about here. So I'm going to come right over here with it. And there's a 45 down here, so I'm going to bring my line down to there, and I can exit there. So here's the rest of the 45 degree isotherm. Now your job is going to be to draw on the 55 and 65. All right, I'll help you get started with those. 55, we kind of find on the map that all the areas right here are actually colder than 45 degrees. So my 55 degree isotherm is going to be somewhere in this area here. We can kind of start in the middle again, like we talked earlier. 52 and 57 gives 55 right about between them right here. Same 52 and 57, 55 is going to be right about there. Between 52 and 61, 55 is going to be closer to the 52 over here. 61 and 45 would put 55 right about here. So you can see my line starting to form. Okay. Between 61 and 61, nope. We know that 61 is here and 42 is here. Where would be 55? It would be right about here. So my line's coming down here. 44 and 66 would put 55 right about directly in the center, so I'm coming in there. Same, 46 and 63, we'd have 55 right about here. And it looks like it probably trails off that way. It might actually curve this way because the 45 curved that way, so we might curve it that way as well. But this is the 55 degree isotherm and where it comes off the map there. Again, then I'm going between these. 57 and 36 is going to have 55 close to here. And then we have 57 and 54 here. So 55 is going to be closer to right about here. So we're coming this way with it. 54 and 66 would have 55 right next to the 54, so we're coming here. 54 and 66, 55 would be there. And 45 and 66 would have 55 right about in the middle. So the 55-degree isotherm comes off the map here. Okay. Can you draw on the 65? Hopefully you can. I'm going to leave you to 65, and I'm going to leave you to answer the questions on the bottom. All right? All right, the next section here deals with air masses, and of course, the warm air and cold air that we mapped out with isotherms in the last page, the last section, is coming from somewhere, and the air above a particular region takes on the characteristics of that region. If the air is above water, it's going to be more moist. If the air is above land, dry. Likewise, if the air is in a colder area, developing over a colder area, it's going to be cold. And if it's developing over a warm area, it's going to be warm. And so we have particular denotations for the different types of air pockets we call air masses. And here they are. Maritime equatorial would be, and they're given with the moisture level here in the first as a lowercase level, so or lowercase letter, so moisture is given there, and then temperature is a uppercase as the second letter, so this would be temperature. Okay, so this is maritime environment, so this would be a moist air mass, and equatorial means near the equator. That's going to be a really, really hot air mass. Okay, likewise, these maritimes are moist air masses, tropical would be warm, and polar would be cold. And likewise, continental, tropical. Continental is going to be dry, so each of these is dry air masses, with tropical warm, polar being cold, and Arctic being very cold, okay? And what I'm asking you to do is to put the symbol for each of these air masses in the map given here below, okay? So first of all, we can note is that Arctic air masses are cold, and very cold, and polar air masses are semi-cold. So the ones coming from this region are going to be polar, whereas this is Arctic. Okay. Likewise, then the moisture level over this region. Now this region is tricky. This is going to be continental because it's mostly ice up there, ice pack. So that's why I'm doing that one for you. And then this one here, this is of course over the continent of Canada, so it's also a continental. So the symbols here are going to be CA and CP. Okay. Likewise, this one is over probably some water, not yet to that ice pack just south of Greenland there. So we're going to call that maritime. And of course, it's coming from cold, so it's polar. Okay. From this information, you should be able to tell what this one's going to be. So I'll leave that one to you. Okay. Likewise, in the south here, we have regions of warmer temperatures, of course. So, for example, the air masses down here are going to be tropical. We're not far enough toward the equator to get equatorial. So this is also going to be considered tropical here because the Gulf Stream is warm water coming up from the south. So those are tropical air masses. We have a continental variety here, and that's forming over the Mexico land mass, whereas this one is forming over the Gulf of Mexico. Now, very interestingly enough, this Mexican dry, warm air mass actually intrudes in and usually hangs out in the south by Texas and Oklahoma, and it forms what we call a dry line. And when you hear the word dry line, it's a forcing mechanism for tornado formation. So we'll talk about that maybe later on in this class. And the maritime tropical air mass over the Gulf of Mexico is usually responsible for most of the moisture, warm, moist air that comes up and causes clouds and storms because this sits over the top, and this continental polar air mass from Canada gets funneled down through the central part of the U.S. by the Rocky Mountains. And so this comes plowing up. It's more dense, so it plows up that warm, moist air and causes clouds and storms all through the central part of the U.S. So much so that the central part of the U.S. is called Tornado Alley. 70% of all tornadoes in the world occur right here because of this perfect storm of warm, moist air, which is the fuel, and cold, dry air, which is the plowing mechanism or the lifting mechanism. Okay, we have a maritime tropical air mass over here. I'm going to leave these two air masses to you. But air masses are important because they are ultimately the clashing of them is ultimately what causes our weather here in the central part of the U.S. Fronts are the boundary between two air masses. So the air masses we discussed in the last page, for example, this one, this scenario here, you have kind of a cold, dry air mass. So that would be continental polar air mass up here. And your warm tropical air mass down here would be maritime tropical, okay, from down here. And you can see the wind barbs blowing in the air this way, like we talked about from Canada, versus the tropical air mass wafting up from the Gulf of Mexico here. The boundary between these two air masses is called fronts. And fronts typically occur between, and you can tell where there's a front because there's a sharp temperature gradient. You'll find a very sharp temperature gradient here. You'll have a sharp moisture gradient, noting that, for example, this is like, for example, it's 46 degrees with a moisture of about 56 degrees, 45, 33, 49, 37. These are low temperatures and low moistures. You compare that, and these as well. You compare that with, say, this one was just 61 degrees and a 57 degree dew point, meaning it's a little bit more moist. Comparing that to the 49, 41, they're different, significantly different. And so sharp gradients in temperature and moisture, and even changes in wind direction, noting that these winds are blowing this way and these winds are blowing this way, you have a front, okay? And so the front, the boundary between the two air masses, is indicated by certain symbols. For example, you're asked to draw on a front here to show the contrast between this air mass, which is coming this way, and this one, which is blowing up this way. And so you're asked to draw a line here. And I know that this is a cold front because the air behind it is colder and drier. And cold fronts are shown by a line with blue line with blue triangles. So you'll note that the wind barbs are blowing this way, and so too are the triangles pointing this way, showing that the cold front is moving in that direction. Likewise, we have the warm front, and I already drew it in. My video got interrupted by a phone call, so I had already drawn it in here. But I wanted to show you that this warm air mass is wafting this way, and the front of that warm air is right here. And so we draw in a line here, and the warm front is given by the half circles in red, as you can see pictured here. And typically the warm front meets the cold front, and where that happens, air actually starts to swirl upward. And so we'll deal with that idea. It's called low pressure. We'll deal with that idea in the next section. So in this section, we're going to focus on pressure. And pressure is measured and given because the pressure of the air helps us determine whether the air is descending or rising. If the pressure is lower, that means the air is rising, and where you have rising air, you have clouds and storms. So this is useful information. Where you have air descending or coming down, you're going to have higher pressure and you're going to have clear weather, because rising air equals clouds and storms. So in this section then, we want to draw in some isolines so we know where the pressure is lowest and where it's the highest. And remember, our isolines are drawn in between areas of pressure at usually about 1,000 millibars, 1,004 millibars, 1,008 millibars, 1,012 millibars, and this is at every 4 millibars as we go through. And typically the lowest pressure area on the map is given a big red L, and so we're going to do that today with this. Now remember, when pressure is given, it's given with just 3 numbers, and you have to do some doctoring on those numbers to get them to where you need them to be. So for example, if we start in the upper left here of our page, remember a decimal point goes in between the last 2 numbers, and a 10 or a 9 is added to the front. A 10 if the number is less than 50, and a 9 if the number is more than 50. Okay, so I went in and written in all the pressures so that we can kind of better interpret them. It's usually better to kind of have that available rather than trying to interpret them in your head. It makes things more clear. And we're supposed to draw in isolines of 1004, 1008, and 1012. So we'll start with 1004. And with 1004, we're going to find areas that are between 1004 and below. So in this case, for example, we can kind of look around the map and see where we have lower pressures. And I can see that there's 1004.4 here and 1002.9 here. So right in between these is going to be 1004. In fact, I would probably put a little X right there to indicate where the 1004 would be, the 1004.0. Likewise, between 1002 and 1009, 1004 is going to be somewhere like right around here. And between 1002.9 and 1012.4, it's going to be closer to here. And we keep going. 1002 and 1013, we would have 1004 right there. 1002 and 1008, 1004 would be right about here. And then we have 1002 and 1002, so we're going to hop to this one. Between 1002 and 1008, 1004 would be somewhere right around here. 1002 and 1009, we'd have 1004 right there. This is 1002 and 1002, so that's not going to work. We're going to jump to this one real quick and see between 1002 and 1009, 1004 would be right about there. 1002 and 1008, 1004 is here. 1002, 1006, 1004 right between them. And 1002 and 1004, 1004 is going to be closer. So here we've got a little area here where we're going to just connect our X's. We didn't go off the map this time. We actually went in a circle if we're going to connect all those. So in this area right here is below 1004. And then this is the 1004 line. Okay, for pressure. So below this is less than, and above this is above. So we're asked to draw in a big L to represent the lowest pressure. And right where then Iowa, Illinois, and Missouri meet is where I might draw a big red L to indicate that there's the lowest pressure on the map is right here. And if indeed we can kind of look around and see that. Okay. The next level up then is our 1008 millibar line. And when we're looking at that, we started here in the middle, so 1004, so 1008 is going to be somewhere out from that. In fact, here's 1008.8, so just above 1008, so I'll put an X right next to that. We have 1010 and 1006 here, so 1008 is going to go right in between those. So I'm going to come this way. Going back the other way for a sec, 1002 and 1009, 1008 is going to be closer to 1009, so I'm going to come this way. So you can kind of see it's probably going to be a circle likewise to the other. Between 1009 and 1000, this one's 1008.4, so we're coming right here, close to this one. And between 1015 and 1008.4, we come right here. 1008 and 1013 is right here. 1012 and 1008. This one is 1008.4 and 1009, so right in, it's going to be kind of closer this way. Let's see here, 1002 and 1012, 1008 would be right in here. 1002, 1004 and 1009, 1008 is going to be closer to here. So you can kind of see this take shape, kind of winds around this one here, comes this way. We keep going. Between 1004.4 and 1009, 1008 is going to be closer to this, so we're going to kind of come this way with it. Let's see here, between 1004 and 1014, 1008 is going to be somewhere here. This one is 1007.5, and this one's 1011, so 1008 is going to be somewhere here, so we're going to kind of come around like this. Between 1012 and 1007, 1008, 1007, 1010, 1008. It'll be right about here. And so we can kind of connect our lines. And there we have it. That's our 1008 millibar line. Okay. So we can actually see our zones here. 1000 below 1004 would be like right in this zone here, right? And this area between 1004 and 1008 is where we're going to have everything in between. So this is kind of its own little zone, right? And they don't usually color these in on maps. They usually just leave the lines. But the pressure then is telling us that this pressure is low on the surface, and the pressure outside of it is higher. And when you look at the isolines, the air is kind of flowing into that low pressure, and it's coming up and swirling in. And so air swirls into low pressure like a toilet bowl, and it actually flushes upward. Okay, so the air actually hits together at the surface, and because it's rushing in and the pressure here is low, if you were standing here, there will be less air molecules on you, around you. That's because the air is swirling upward because of it's swirling because of the Coriolis effect, and it's moving upward. So it's like a toilet flushing upward of air molecules. So the air molecules are rushing in and rushing up. Remember what I said happens when air rises? Rising air equals clouds and storms. The air rises, cools, condenses, and forms clouds, and that of course forms precipitation. So anywhere you see these low pressure, you're probably going to get clouds and storms on a weather map. And of course, as the pressure is low, you're going to continue to get that. I'm going to leave you to draw in the 1012 millibar line and then answer these questions about isobars and pressure. All right, this part is looking at wind and the direction of general wind flow. And those are given by wind streamlines, which are just big arrows showing the wind direction. You can see here, all the wind barbs are pointing this way. That means the wind's coming from the northwest and going towards the southeast. And so you got a little arrow showing that. Likewise, you can see the flow of air going this way. I've asked you to add in 5 more wind barbs, okay? So you might draw in wind barb that comes in like this. You can see the air flows this way. And then you might draw in some another wind barb that comes up this way, or a wind streamline that is, excuse me. And then you can kind of see how the wind barbs are flowing. Remember that low pressure we showed on the last slide? These are all the same kind of weather patterns. Notice how the wind is swirling into that low pressure area. And again, as it swirls in, it swirls upward, drains upward, and that causes clouds and storms. Okay, here it is. It's go time for you. I'm going to have you go through and interpret a surface weather map. Now you're going to draw in all of the required information here, and in the end, it's basically going to be a combination of all the separate parts we just went through together. I'm going to ask you to draw in isobars at 4 millibar intervals at 1004, 1008, and 1012 on this map. Remember, you're going to write out the pressures, okay, for each. For example, on this top upper left one, you're going to write a 10 in front of it and put a point between the last 2 numbers. You're going to go through and do that for all of them, and you're going to put in your X's for the 1004 millibar, 1008 millibar, and 1012 millibars. You're going to then put a big red L for the low pressure where that occurs. You're going to draw in then, in a separate section, you're going to draw in the warm front in red and the cold front in blue. So the front of the very front edge of the warm air barbs, you're going to draw red, and the front edge of the cold air barbs, you're going to draw a blue line. You're also going to label those air masses. You can go back and look at the air mass section and the weather front section for what the air masses should be labeled. I did that earlier. And then new to this map, you're going to shade in the areas receiving precipitation in green. Remember those weather map symbols? The 2 dots showed light rain. I even showed you the R, that means thunderstorm. So you're going to draw in maybe a little bit heavier rain in that location, a little bit darker green. But you're going to draw in and just kind of shade in the areas that are raining. And bada bing, bada boom, you have created a surface weather map. Now remember, the purpose of drawing a surface weather map is for us to see visually on a macro scale what the weather is doing over a large region. And when we kind of compare that with past weather patterns, we can see the weather patterns, and it helps us predict future weather systems. So try your hand at this and see how it goes. If you have any questions on this, please do not hesitate to email me and ask. Well, I hope you enjoyed our lab on weather today. Nature is amazing, isn't it? How air molecules get together and they crowd together or separate themselves, and that, of course, is pressure. How fast and how much energy they're distributing, that's temperature. And how many water molecules are thrown into the mix, that's humidity. And together, those create our weather systems and the weather we see out there every day. It's all about all the molecules distributing their energy equally. And it's just really neat to see how the physics of all this plays out in our atmosphere and the things we see. And of course, all this weather stuff is so that we can predict weather and see what's going on in the future for our weather, so we can plan our weeks and our days and all those things that we have going on in our lives. So it starts with creating surface maps, first of all, measuring the weather conditions, then putting that onto a surface map, looking at those past surface maps, recognizing those patterns, and being able to then forecast the weather. So I hope you learned a lot from this today, and we'll turn our attention to severe storms moving forward. Take care and have a great week.